again on our journey through Malware Analysis Fundamentals. As you can see by looking at the desktop here, you can probably guess that today we're going to talk about hashing. So hashing is going to be a way that we can take multiple pieces of malware or even files themselves. It doesn't necessarily have to be malicious software, and we're going to be able to fingerprint those files, and it'll be just like the fingerprint on a person, right? Each person has a unique fingerprint. So when a crime is committed, we can take those fingerprints and look at them and compare them to an existing database of other hashes, or we can use it as an indicator of compromise when another crime is committed. So hashing is basically a cryptographic function that takes the input from a file, runs it through a complex algorithm, and spits out a string of digits and numbers, usually A through F, and a series of numbers. The length of the hashes differs based on whether it's MD5, SHA-1, SHA-256, SHA-384, or any number of other algorithms. Generally speaking, today we use SHA-256 to fingerprint files, and we'll get into why just shortly. So I've got a number of exercises for us today regarding cryptographic hashing, but I also have a good exercise for us about when cryptographic hashing isn't enough, which is more and more recently because adversaries are implementing something called hash busting, which is where an adversary can take files and through a complex series of things like flow control and state-dependent code sort of change things so that the output of a cryptographic hashing algorithm is different every time. So that makes it more difficult for them to be accused of something or for them to receive attribution for the malware that they're distributing, just simply because it can't be done via hashing, which has historically been a very popular way of attributing malware and tracking adversaries. So without further ado, we'll go ahead and get started. Okay, so the first thing I want to talk about today is why we use SHA-256 generally as our current go-to when it comes to hashing files and utilizing that as a fingerprint as opposed to something like, say, SHA-1 or MD5. Well, the answer is a little complex, and we won't get into the intricacies of the cryptographic hashing algorithms because I firmly believe that cryptography is just math designed to make you feel sad. Instead, we'll just talk about what has happened to move us away from MD5. So in hashing, there is something called a collision. In a collision, what can happen is that two files, which are actually different, have different content, will produce the same hash. So that's kind of a problem because one of the fundamental tenets of hashing is that if even one bit of a file changes, it produces an entirely different cryptographic hash. That is important. We want each hash to be totally unique for each file. Even if only one bit changes, we want a totally different hash. That is the absolute fundamental of fingerprinting and hashing files. However, that's not the case with MD5, and several attacks have been discovered that have caused collisions. You can see that I have two files here, and we'll demonstrate that just shortly. However, you may be asking, fine, MD5 is broken, but why not just use SHA-1? Well, it's kind of got the same problem, right? Some similar attacks have been observed against SHA-1. Now, I don't think it's quite as broken as MD5 is at this point. MD5 probably has far more vulnerabilities in its hashing algorithm than, say, SHA-1 does. However, it's easier to just move to SHA-256 because at that point we go from 128-bit hash that is produced and represented by hexadecimal characters to a 256-bit hash that is produced and represented by hexadecimal characters. So let's go ahead and take a look at how that's going to work. So we'll open up a program that comes with Flare here. You can see it on my desktop. It's called Hash My Files. We'll go ahead and open that up, and we'll drag over first md5-1.exe and drop that in there. We can see we've got an MD5 of 66.5ff are the first 5 characters there. Now let's grab MD5-2-exe. Okay, So you'll note that 665FF1DD, that is an identical hash. Absolutely identical. However, you will note that the SHA-1 is different, as is the CRC32, the SHA-256, the SHA-512, and every other hash in here. So it would stand to reason that this is a good indication of a collision within MD5. We have produced the exact same hash with two different files. We can actually go and confirm that by opening it with some sort of hex editor. So we'll just open it with 010 editor and take a look at the two files side by side. Okay, so once we've actually got these two open, we can take a look here in this hex editor and see that there are some remarkable differences, indicating that this is not at all the same binary. You can see on the right hand side we have an evil executable, which is not good. On the left hand side you can see we've got a good executable. However, they do produce the same MD5 hash. So we'll go ahead and close out of this. I think we've made our point that it is best to use anything other than MD5, but ideally at this point the industry standard is going to be SHA-256. So let's perhaps take another look at something that we can utilize this fingerprinting of files and hashing for. As you can see, we've got a file in our folder here called sample.dll. Obviously it doesn't have a name to it, no attribution, we just know that it is a sample of a malicious program. We don't know what though. So we could take a look at some other static analysis techniques and see if we could obtain some characteristics of the file that would maybe indicate what sort of malware we're dealing with. However, in this video, we're going to be talking about hashing. So let's go ahead and just get it open with hash my files. Okay, so with it open in hash my files, we can see that it has returned an MD5, a SHA-1, and several other hashing algorithms. So for this, we'll go ahead and copy the SHA-256 out to our clipboard. We can now take that hash and use a tool like VirusTotal to see if we can obtain some attribution here. So we'll go ahead and paste that in and search in VirusTotal. Okay, so it looks like this file's been seen before. Some community comments on it. Joe Sandbox seems to think it's malicious. If we scroll down a little bit, let's see if we can get some attribution here. Looks like it may be something called Polizert. Not familiar with that one. Let's just go ahead and Google that. So if we take that information that we've obtained from VirusTotal and go and Google that, we can see several different things here. We can see results from Twitter, which is a wonderful place for threat intelligence, as I'm sure you may know at this point. It's excellent to follow people on there and find the latest and greatest in malware. You can also see some results from Alien Vault, which is also a really good place to find the newest things about any sort of malware, really. New IOCs, new C2 servers, things of that nature. But if you look through this, you can see that it is also tracked as Solar Marker, Jupiter, Yellow Cockatoo, and Polizert. So it's a remote access Trojan. So if we go and read this news article, that's probably going to give us some valuable information. And if we found this within our environment, we may know exactly what we're dealing with and maybe what even threat actor it came from. That is going to be the value of cryptographic hashing. Okay. Let's talk about another way that we can utilize cryptographic hashing in order to fingerprint things. Hashing is not just limited to whole files. We'll get into more detail later, but there are several sections within an executable's header in the Windows portable executable format. Sometimes what we can do is we can take the hashes of these sections and utilize them as fingerprints if other sections have changed. So let's go ahead and open up a tool called PE Studio that I've included here for you today. We'll be using this tool a lot more later on. As you can see, it wants us to drag and drop a file in for analysis. So we'll go ahead and go back to the parent folder and drag in our sample.dll. Alright, so ignoring the rest of this, we'll just navigate directly to the sections and we will wait for PE Studio to complete its work. Okay, so as you can see, PE Studio has returned 3 sections here for us within this binary and a corresponding hash for each section. Again, we'll go into these sections more in detail a little bit later. However, you can see that there's a .text, .resource, and .reloc section. So each section has a corresponding MD5 hash. I realize I said that MD5 is not ideal, and I stand by that statement. However, that's just what PE Studio returns the section hashes in. And balanced with everything else about the program, it's still a really great tool. So we're going to give it a pass this time. The important thing is that you understand that this is where the code lives, and this is where all of the resources that the application uses to execute, be it an icon, a scroll bar, a cursor, something like that. Any sort of resource that the application uses that can't be included within the code section is going to be included here within the resource section. So with that said, if we look at the hashes of these, we can see that they differ. But the important thing to note is, even if, let's say, the threat actor makes a GUI program, let's say it's a ransomware affiliate tool, and they utilize that to click and encrypt an entire hard disk, whatever the adversary may be doing with it, but it's got a GUI. Let's say they change the icon for it, they change the cursor, they change the layout, they change everything about the way the application looks, but they don't change the way that it works, and they don't change the code that it uses. The section hash for the .text section is likely going to be the same as it was. Even if the adversary attempts to change other sections around, we're still going to have the same hash for one of the sections, right? The idea is to use these section hashes as perhaps an indicator that you're dealing with the same code or the same binary, just changed in minute ways in other sections. Okay. So up to this point, we've only talked about static cryptographic hashing. That is to say, hashing algorithms like MD5 and SHA-256 that change the entire hash whenever a single bit or more is altered. So each time we flip a bit or change a single thing about the file, so even if we changed any single number that appears within the hex of the file, we would get a totally separate hash. However, that wouldn't really change the functionality of the program, generally speaking. So with that in mind, a threat actor could, theoretically, flip a single bit within their program and get a totally different hash, making it very difficult for us as analysts to utilize the hashing algorithms we've discussed to this point for attribution. As a matter of fact, one actor implemented this within the past couple of years. I want to say it was last year sometime, and they call it hash busting. So what we're going to look at is how, in the absence of utilizing cryptographic hashes, we can still determine whether or not there's a similarity to the methodologies or the previous binaries utilized by a threat actor. For this, we're going to use something called fuzzy hashing. So what fuzzy hashing is a way to take a file and the characteristics of that file and sort of meld it down into something that is not as static as cryptographic hashing. It presents a fuzzier picture, right? So you take these two fuzzy pictures and you say, okay, if I don't look at the minutia of each of these, do they kind of resemble each other? That's a good way to think about it, I think. So there are a couple of different hashing algorithms that do this. There's imphash, there's ssdeep, and quite a few others, to be frank, I think. However, I'm most comfortable with ssdeep, and I find it has the broadest base of support, so that's the one we're going to use today. Now, for purposes of this, I have included a copy of ssdeep within the folder that is in the description below. Now, it is a couple versions back because I just noticed this morning that there is a bug in ssdeep 2.14.1. I'm going to do my best to try and fix that one, actually, I think, see if I can do a little pull request on GitHub. But it looks like it has some trouble with the database and comparison, and I really wanted to show you guys that, so we're using a slightly older version. So within the folder here, you can see we have two files. We've got emotet1 and emotet2. These are both live samples of emotet, so please do be careful. Do not execute these. We're not doing dynamic analysis yet. If you do execute them, just restore back to the snapshot that we took back in the first video, and you should be fine. However, let's take a look at these first within HashMyFiles. So we'll click on both of them, and we will right-click and open with hash my files. So as we can see here, we'll just scroll on over. We've got two different files. SHA-256 starts with F97 on this one, and on this one it starts with 871. So these are very clearly two different files, right? At least one bit differs within these files. So it may be very difficult to obtain an attribution like this, or to hunt for that hash in your environment. If several phishes were sent out that day, you can't just simply utilize a PowerShell script to look for one hash, just because there may not be just one hash, right? Each hash on each machine may be totally different based on how the operators sent out the phishing emails that day, or any number of techniques or tactics that they've utilized to do that. So it may greatly lower the efficacy of your hunting operation. That is where SSDeep comes in. We can utilize SSDeep to obtain a fingerprint of the first file, put it into a database, and then compare that file for similarities to the other executables. So the first way that we can do that is we're just going to go up here, and this is a nifty little trick I learned a while back. You can just click in the top of the bar, type in, let's go with PowerShell, and it will actually open it at that path. Very handy trick to know. Okay, so I know in the last little section there I was opening up PowerShell instead of command prompt. However, I'm not a big fan of cutting out mistakes, so I want you to see that it's pretty much constantly a learning experience in malware analysis. So what I learned was the bug that I was talking about was actually my fault. It was not related to SSDeep's implementation or any bug within the program itself necessarily. It appears that when you use PowerShell, it may introduce some funky line endings in there that makes SSDeep not recognize the actual header on the DB that you create. So with that said, we're now in command prompt, and we're going to be looking at how we can do this. So avoid PowerShell with SSDeep at this time until I can figure out exactly why it's doing that. No big deal, we can just use command prompt. So with our command prompt open at our path, what we're going to do is we're just going to type ssdeep, and we'll do emotet1.exe first. So as you can see, ssdeep is going to return kind of a long hash here, and up at the top it actually tells you what this hash represents, right? So we've got block size, :hash, and then comma the file name that we actually hashed with ssdeep. Now, it's not really necessary that you know from a technical perspective how SSDeep works. We're not going to be diving into that here. However, I will put a link in the description below for those of you that are interested in learning exactly how SSDeep makes these correlations between files that cryptographic hashing algorithms would generally have difficulty with. But again, not necessary for us to understand that to understand malware analysis and how SSDeep applies to that. So we've put it out to the terminal. We know what the SSDeep hash is, but we need to store that somewhere. So for that, we'll do ssdeep emotet-1.exe, and then we'll redirect that output using the, I suppose that would be the greater than sign, and we'll redirect that to fuzzy.db. Oh, darn. Mistyped it. All right, we'll go ahead and ssdeep this time instead of sdeep. All right. So let's go ahead and check out our fuzzy.db and make sure that it worked correctly. It sure did. So we now have that information, the same information that was returned to the terminal, except now it's out in a file. So now that we have the hash stored for emotet1.exe, we can go ahead and do this. We can do -m fuzzy.db, and the -m switch just directs it to match to anything that we've previously put into our file. So -m fuzzy.db, and then emotet2.exe. And you can see that it returns here. Emotet2.exe matches this file, emotet1.exe, with a 99% match. So very little has changed in the file. However, as we said, just a tiny fraction of that file changing is enough to totally change its cryptographic hash for static functions such as MD5, SHA-256, or any of the hashes like that. However, SSDeep is still able to make that correlation. Now, there are more options available to us with SSDeep. If, for instance, we wanted to actually store the fuzzy hash of the second emotet binary just in case there was another binary out there perhaps stored on one of our user systems that was based on the second binary but perhaps was changed from that one, so it was quite dissimilar to the first one but not so dissimilar from the second one, and so on and so on, we can actually do that too. We can just SSDeep, and then instead of a single caret, we'll just append to the end of the file, right? So we'll go back and look in there, right click on that. Where's fuzzy.db? There it is. And we'll edit that with Notepad++, and you can now see that we have 2 hashes within our SSDeep database. So that is a good way to store multiple files. Now, that is not the only option we have. We can actually take this hash, and there are tools that will allow us to search not just the files that we've come across, but the files that many malware analysts have come across. The best one for that I have found is VirusTotal. Now, it does require an enterprise subscription in order to search SSD. I have one of those. You may not. Your employer may provide you with one, but if you do have one, you can do it like this. Just SSDeep, quote, your fuzzy hash, end quote, and then search. Now, VirusTotal will take quite some time to do this because it has a vast database of malware and just files that people have uploaded, and it does create fuzzy hashes of those when they are uploaded so that we can compare them to other files. So it'll give you the similarity, as you can see. So we've got one file that is 100% similar and one file that is 97.83% similar. Now, these would probably both be very close to our first file, but sometimes they're not, and that's okay. That's what SSDeep is for. As you can see, there's about a 3-month difference between these files. One was actually just today it was discovered and uploaded, and the other one was about 3 months ago. Now, this file probably lived on this person's machine for at least 3 months, if not longer, but that's okay. Well, it may not be okay to them, but it's okay to us. What we know now is that if we open up one of these and we scroll down, we can utilize the SSDeep search to know that this is emotet, beyond a doubt, even if there were no static search results for it, utilizing those hashes. This applies to all kinds of malware, not just emotet. Cakebot, for instance, also does that, also known as Qbot. There are plenty of adversaries that perform some sort of obfuscation that keeps them from utilizing the same hash over and over, which in turn increases the longevity of their malware within an enterprise environment, or really any environment, because it can't be searched for simply by static hash. Alright, so quick recap of what we've covered today. I've got a ton of stuff up on the desktop, and we're going to use this to sort of drive home the point that we're talking about when it comes to hashing. So, we first talked about cryptographic hashing algorithms, why not to use MD5, and why to use SHA-256. And we'll use our 2 emotet examples here. You can see that they have differing SHA-256 hashes, which is totally normal for them. We also then talked about getting the section hashes using PE Studio. As you can see here, with our 2 different emotet samples, the hashes for the R data sections are different. However, every other section hash is the same, indicating that these may be good to utilize as an indicator of compromise for this particular campaign, or perhaps for this particular day, depending on how our friends at Mummy Spider have been feeling lately. We then finally talked about SSDeep and fuzzy hashing and how we can utilize that to obtain similarities between otherwise disparate files in cryptographic hashing methods. As you can see here, we've got both hashes for the 2 different emotet files. However, you can see just by looking at them that they are very, very similar. And SSDeep will also tell you that when you run it across the database, which we have also covered. I hope you enjoyed today's video, and I hope that understanding cryptographic and fuzzy hashing to this depth will make you a better malware analyst. We'll be back next week with more static analysis techniques in order to improve our skill set. Thanks. Bye.